All right, so you already know what the product sum trig identities are. These are the sum product trig identities, and you can see the 4 here. Now, deriving them is really, really straightforward. We take the product sum trig identities and we sub in 2 different things. I'm going to derive the sum product trig identities. I'm not going to do all 4 of them. I'm just going to do one, and you can fill in the gaps after that. So, step 1, choose a product sum identity. So here are my product sum identities. And let's just choose the first one and deal with that one. So step 2 here, I'm going to sub in u plus v over 2 and u minus v over 2 for a and b respectively. And don't worry about why, let's just trust the process. You can see I put u plus v over 2 for a and u minus v over 2 for b. And then I've done the same here, 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 and here. Now, cast your eye over this bit. U plus v minus u minus v, both of them over 2. So because they're both over 2, we're going to be able to subtract those 2 fractions. Because they're both over 2, we're going to be able to add those 2 fractions together. And when we simplify it, some of these u's and v's are going to cancel out in some way. Do this next bit in front of you so you can see what I'm doing. U minus u, the u's will cancel out. V minus minus v, that'll give me 2v, but it's going to be 2v over 2. And 2v over 2 is just going to be v. So all of that junk there just becomes v. And then here we get minus cos, and then u plus v plus u minus v. So u plus u would be 2u. Let's keep that in our head for a second. And v minus v, the v's are going to cancel out. So I'm going to end up with 2u over 2, which is just going to be u. Cos u. And so now we have this neat little thing here that says that sine u plus v over 2 sine u minus v over 2 equals half cos v minus cos u. Finally, traditionally with this, we don't leave that half there. Instead, we divide both sides by a half, which is the same as multiplying both sides by 2, which leads us to this result. 2 sine u plus v over 2 sine u minus v over 2 equals cos v minus cos u. And that is one of our sum product identities. Now, if you take a look at it, you might not recognize it on our list of 4 here, and you're right. I've used the letter u instead of the letter v instead of a and b. I used u and v because I didn't want to confuse matters here. But also, if you actually take a look at it, it doesn't look like any of these, but it's actually this one right here. So I'm just going to rearrange it a little bit, and I'm going to do that by moving this to this side, moving that to that side, or adding them to both sides, and then adding that one to this side, or subtracting that one from both sides as well. And it's going to look something more like this now. Just moved everything to the other side, and you can see we have cos u minus cos v, which is cos a minus cos b, and we have negative 2 sine u plus v over 2 sine u minus v over 2, which is exactly this, with u's and v's instead of a's and b's. Okay, you can derive the other 3, this one, and this one, in exactly the same way, just by subbing in u plus v over 2 and u minus v over 2 into the other 3 product sum identities. Now, of course, the question now is, now that we know that it works and now we know where it comes from, what are we going to do with it? The thing we can do is express a sum of trig functions as a product of trig functions. And it's going to be as simple as taking a look at our sum, sine 36 degrees plus sine 10 degrees, looking for our identity, this one right here, sine A plus sine B, and then subbing in our values 36 and 10 for A and B, what I originally called U and V when I was working through my derivation. Subbed in 36 and 10, 36 plus 10, 36 minus 10, and I'm going to divide them by 2, and that's the end. It's 2 lines of working. That's it. That's one thing that you can do with these. Now, why would I want to write a sum of trig functions as a product of trig functions? Well, there's a great reason. Let's try to solve this equation. It's a trig function plus another trig function, and importantly, it's equal to 0. Now, this is a sum. If I were to write it as a product, I'm going to have two trig function products. And that means they're multiplied together, right? And if two things are multiplied together and they're equal to 0, the null factor law tells us that the one or the other must be equal to 0. So that's a great reason to be able to do this. Now, looking through my four sum product identities, I see this as sine something plus sine something else. So I'm going to have to use this one again. And I'm just going to sub in 3x for A and 11x for B, and away we go. Subbed that in. Now that 3x plus 11x will be 14x divided by 2 will be 7x. 1 will be 3x minus 11x over 2, which is negative 8x over 2, which is negative 4x. Good start. What we have now is this times this equals 0. Therefore, this must equal 0 or this must equal 0. So we've got these setups now. Now that 2 could have come along for the ride wherever because it's going to vanish anyway because 0 divided by 2, if I divide 0 divided by 2 will be 0 still. So we can just rewrite that as sine 7x equals 0. And if sine of something is equal to 0, then the something must be equal to 0 or pi or 2 pi or 3 pi or 4 pi or 5 pi or 6 pi, etc., etc. Thinking, wait a minute, why are you going so far? Because the domain is only between 0 and pi. But that's the domain for x, not the domain for 7x. So now I know that 7x is equal to this. And if I divide all of those by 7, I'll know what x is equal to. Those are all of my answers for this side of that equation. And now I can do the same here. Tempting here to say that negative 4x is equal to pi on 2, 3 pi on 2, 5 pi on 2, 7 pi on 2, 9 pi on 2. But that would be fine. But when we divide all of those by negative 4, we're going to start getting negative answers. And our domain is between 0 and pi. So instead, let's write our solutions here as negative pi on 2, negative 3 pi on 2, negative 5 pi on 2. I've gone far enough, but let's try that. Negative pi on 2 divided by negative 4 will give me will give me positive pi on 8. Okay, and there's a bunch of answers. Boom, 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 boom. This last one here is a garbage answer. Because 9 pi on 8 is more than 8 pi on 8, and 8 pi on 8 would be equal to pi. So we can reject this because it's outside of our domain. And we finish with x being equal to all of these and all of these. All right, so that's pretty good use. If that was all I could use these identities for, I would be pretty happy because it feels like really useful. But of course, we could also do some proofs. I want to prove this. This stuff on the top of the fraction over this stuff on the bottom of the fraction is equal to tan 2 theta. Now, there's not a lot I can do with tan 2 theta, and usually we want to mess around with the more complicated side than the more simplified side. Now, we can't really split this fraction up at the moment, but if we can create products top and bottom of this fraction, maybe some of those products would be equal and we could start cancelling them out. So I see two useful identities for me to use here. So I can use the cos, the minus one here, and sine the minus one here, and I can sub in theta and 3 theta respectively. I think so will lead me to this. Just be aware that on the top side, theta was our A value and 3 theta was our B value, whereas on the bottom side, 3 theta was our A value and theta was our B value. So they were reversed top and bottom. Okay, from here, we can simplify that stuff, simplify that, simplify that, simplify that. We've also got, because this is all a product and this is all a product, I can also get rid of the 2's, cancel them out, and I'll just have a negative up the top. If you stop and take stock for a second, you should be looking at sine 2 theta and looking at cos 2 theta and saying, well, if it was just that over that, that would be tan 2 theta, and I would be finished because that's what I'm trying to prove. So it's this thing and this thing that are in the way. And you should notice that they look really similar, but sine negative theta and sine theta are not equal. But lucky for us, negative sine negative theta and sine theta are equal. If you think about it, That's sine theta. There is the y coordinate. That's theta. This would be sine of negative theta, the y coordinate of that thing. Now, if we take the negative of that, we'd be taking a negative y coordinate turning into a positive y coordinate. All of that is to say that we can now cancel out this in conjunction with that and that, which will give us sine 2 theta over cos 2 theta, which is, of course, pretty much the end of the game because sine 2 theta over cos 2 theta is equal to tan 2 theta. Therefore, the left-hand side does, in fact, equal the right-hand side, and this thing has been proven. All right, so that is the sum to product trig identities. We looked at how to derive one of them. You can figure out how to derive the other three. We looked at a really simple idea that you could express a sum of functions as a product of functions. And then we saw why it would be so useful to be able to solve to be able to express the sum of functions as a product of functions, because then you can use your null factor law to solve. And we also saw that it's just another tool that you can use when it comes to proving trig identities.